Okay, so now we can talk about whether a grammar is ambiguous or not. At the end of the day, the main goal of talking about grammars is that computers find them very useful for parsing strings. So, for example, if you have a string of ones and zeros combined with pluses in the middle, i.e. any valid equation with 1 and 0 and plus, end of the day, you'd like the computer to be able to evaluate this. And this can get quite tricky with multiple operators. In this case, ambiguity doesn't matter because the plus sign is an associative operator, but if it wasn't, then we could run into problems. So, first off, what does it mean for a grammar to be ambiguous? Ambiguity. So, grammar is ambiguous if there exists a string that has two different parse trees. And this is bad because if a string has two different parse trees, then the computer is not going to know how to evaluate the string because it can parse the string in two different ways. Okay. So let's look at this example here. S can go to S plus S, or 1 or 0. We want to make a parse tree for the string 1 plus 1 plus 0. We want to be able to do it in two different ways to show that this is ambiguous. Start with this. I go to S plus S. And you can see here I've got a choice. I can either evaluate the left-hand side or the right-hand side. And whenever I have a choice, that's what's going to give me ambiguity, right? So here I can choose to evaluate the left-hand side and get S plus S, send this to 1, this to 1, this to 0. And similarly, I can evaluate the other way on the other side. So what this code will do, well, what this tree will do, is it will instruct the computer to compute 1 plus 1 first and then add 0. Whereas this one will compute 1 plus 0 first and then add the 1 on the front afterwards. And again, because plus is an associative operator, this doesn't look like it'll cause any problems, right? But suppose instead we wanted subtraction. So maybe we add subtraction to this. So S can go to S plus S, or S minus S, or 0 or 1. If I have the string 1 minus 1 minus 1, how should I interpret this? Well, because I can create two different parse trees in a similar way to what I did before, S minus S, S minus S, 1, 1, 1. If I try to evaluate this expression using this parse tree, what would I get? So 1 take 1 is 0, and 1 take 0 is 1. Whereas if I evaluated it in the other direction, because the tree is ambiguous, 1 take 1 is 0, 0 take 1 is negative 1. So I get different answers depending on how I'm parsing it, right? So this is a problem. We don't want our grammars to be ambiguous. We want to enforce a strict both order of precedence and associativity. So when we see this expression here, what we really mean is 1, this is basically equivalent to 1 plus minus 1 plus minus 1. So we really want to evaluate this in a left associative manner. Compute 1 minus 1 and then subtract 1 from the result. So how can we do that? We want to enforce that you can only sort of branch down the left-hand side, while the right-hand side can only ever go to a number. So we could replace this grammar here with something of the form S goes to S plus T, or S minus T, or 0, or 1. Or epsilon. And then T can go to 0 or 1. Okay, so this sort of enforces a choice on where I can branch, because now I can only branch on the left-hand side. So if we try to make a parse tree for 1 take 1 take 1 again, so S goes to S take T, and here I'm constrained, this T has to go to a number. It's going to have to go to 1, which means I have to branch on this side. It goes to T, goes to 1. So I was forced to go to the left-hand side, which implicitly means that the subtraction operator by this grammar is enforced to be left associative, which is the property that we want. Now the problem is I can still get ambiguities depending if I do the plus first or the minus first because they're on the same level, right? So for example, if I wanted the string 1 plus 1 take 0, I can actually evaluate this in two different ways. I could do the plus first, S plus T, and then the, not quite, I've lied actually. Because it's left associative, this will be unambiguous, but the problem is it doesn't tell the computer it doesn't enforce an order of operations. It just evaluates left to right. And this could be bad, right? For pluses and minuses, this isn't going to cause a problem. But if we add multiplication to the mix, suppose I have like, I don't know, 6 times 3 plus 1 times 7. I don't want this to be evaluated to left to right. If I evaluate this left to right, I'm going to get 6 lots of 3, which is 18, plus 1 is 19, times 7 is whatever that happens to be, 19 times 7. Whereas if I evaluate in the correct order of precedence, I should get 6 lots of 3 is 18, plus 1 lot of 7 is 7, which is going to be 19, 20, 25. Right? Which is 25 is clearly not 19 by 7. So I don't want to evaluate left to right. I want to evaluate in such an order such that the order of precedence is respected. So suppose we have a new gamma that's defective. So S goes to S times S or S plus T, S plus S or 0 or 1. So this can generate equations with multiplication, addition, zeros and ones. But this is no good because, again, we can get ambiguous things and, again, we can get things that don't satisfy the order of precedence. We want to do the multiplication first and then do the addition afterwards. So how can we repair this? Well, we can make it left associative, as we did before, by ensuring you can only have a branch on the left. And we can enforce order of operations by doing the addition at the top, so doing the additions first, and then doing the multiplications in the second layer of production rules. That way the multiplications will be at the bottom of the tree, and they'll be evaluated first. So for example, we can have S goes to some number plus S, or the next layer T, and then T will go to some number times T, or the next layer U, and then U can only go to either a number, or it can go back to the top, but forced to be in parentheses. So really I should have written the top. I can include brackets. So if we try to build a parse tree for 1 plus 1 times 0, the parse tree will ensure the multiplication will be done first. Let's have a go constructing it. So S will go to N plus S. N, I haven't written N, whoops, N goes to 0 or 1. So this N's going to have to go to a number. With the left hand side to be 1, so it's going to have to go to a 1. I want to evaluate this S. I want a multiplication, so, well, I can't get a multiplication directly. I'm going to have to go through T first, and then add the multiplication. And then this N is going to go to a 1. And then I don't want any more operators, so I want to send this T to a number. So T can go to U, U can go to N, and then N can go to 0. So here, the parse tree is non-ambiguous, or unambiguous, and also it enforces order of operation. It enforces that multiplication binds tighter than addition. And similarly, if you wanted to add exponentiation, so for example, suppose I wanted more things, I wanted also exponentiation, and exponentiation binds tighter than everything else, so do exponentiations, then do multiplications, then do additions. We could also rewrite this using an additional layer. So I could do the additions first, and then do the multiplication layer, N times T or U, and then do the somethings, do the exponentiations. So N to the power of U, or in the bottom layer. So yeah, addition, multiplication, exponentiation, and then if I really wanted to do the addition first, I can then sort of go all the way down, put a set of brackets, and then go back to the top again. So I can put S in brackets, or I can go just straight to a number. Okay, and then N in this case will go to 0 or 1. Okay, so if I want the parse tree for 1 plus 1 to the power of 1, I can enforce that the order of operations here will be respected by sort of working all the way down to the brackets, then going back to the top again. So I want a addition, but I want the addition inside of brackets. I'm going to have to work all the way down to get there. So S goes to T, goes to U, we'll go to n to the power of u, well that's no good. I sort of want the brackets first, so let's put the brackets. So u will go to bracket s bracket. Oh, that's no good. I'm not going to be able to include my exponentiation, so it looks like my grammar is faulty, right? Because I'm not going to be able to add something in the right-hand side of this bracket. So what went wrong? It looks like having the n by itself is not ideal. We want to sort of go down to the next layer instead of going down to n, because I don't want a number on the left-hand side. I maybe want an equation on the left-hand side. So that didn't work. Let's try s goes to the layer down plus s, or t, so that way this whole thing could be a whole entire expression. T can go to the next layer down, u times t, or next layer down directly. U can go to next layer down times with exponentiation, so v to the power of u, or v. And then v can either put a number, or maybe I'll have n, or start again with brackets. And then n can be our numbers. Okay, so let's give this another shot. So I want to get the addition in brackets and exponentiation. So I need to work my way down to the exponentiation. T, u, v to the power of u. This u here I want to be 1, so I can work my way down. U goes to v, goes to n, goes to 1. I want this v to go all the way back to the top again. So v goes to left bracket, s right bracket. So we go back to the top. T plus s. I don't have a choice in which to branch because this t is going to have to go to a 1 and this s is going to have to go to 1. So t, if I branch any other way, I'm going to add more stuff that I don't want. So t goes to u, goes to v, goes to n, goes to 1. V, n, 1. And this s is going to have to stream all the way down to 1. So s to t to u to v to n. I'm sort of like compacting this tree into 1. So the tree is a lot more laborious and lengthy than it would be using this grammar here. If I was using this grammar here, how would I produce this tree? Well, very easily, in fact. S goes to exponentiation. And then this is going to be brackets. And this is going to be an addition. That goes to 1, that goes to 1, and that goes to 1. Not going to be very hard to produce another version of this pass tree. I can just like swap the exponentiation and the addition in the order that I do that. So clearly this thing's going to be very ambiguous. When the computer attempts to evaluate it, it's not going to know whether to do the addition first and multiplication first. Whereas here it's a very strict ordering. Do this first and then combine it with the exponentiation afterwards.